Back Physics 30. This is the second part of the FI1 unit, FI1.2, gravity near the Earth's surface. So what we'll be doing here is determine the magnitude and direction of the gravitational field strength G at a distance r from a body of mass m. So we're used to finding little g, right? 9.80 meters per second squared, and that's considered to be at the surface of the planet Earth. So if you just take the radius of the Earth into consideration, that's what the gravitational field strength is, approximately on the Earth's surface. But what happens if you go above the Earth's surface and keep going further and further away? That gravitational strength is obviously going to decrease and decrease. So this will look at how, in fact, we figure that out. So when the universal law of gravitation equation is applied to the gravitational force between the Earth and an object at its surface, m1 becomes the mass of the Earth, me, and m2 becomes the mass of the object. So when we're looking at this and figuring out the force of attraction, we have the Earth, of course, so that could be m1, and then whatever it is we're measuring right here, that would be m2. So m1 becomes the mass of the Earth, m2 is the mass of the object being considered. And of course, if I'm looking at just something being at the surface of the planet, I'm looking at radius of the Earth. So the r, the radius of separation, would just simply be the radius of the Earth. This force of gravity to the Earth is the weight of the object on Earth, which can be written as Fg equals mg. So from before, so we can write down here, from before, Fg equals mg. So F with the subscript g, force of gravity at the surface of the planet. We did this earlier in an earlier unit, mass times negative 9.8, right? 9.80 meters per second squared. And of course we have their new way of figuring Fg between any two masses at a certain distance using mg, or the big G, sorry. So if we have this force of gravity and this force of gravity, if I set them equal, Fg equals Fg, then I have mg is equal to big G multiplied by mass of the object, multiplied the mass of the Earth, over the radius of the Earth squared, or the radius of separation. The masses m on each side of the equation will cancel, so the mass of the object itself being measured, we can see it cancels out. And we get G is equal to mass of the Earth divided by the radius squared of the Earth, or whatever distance we're talking about. If we have an altitude, we would simply add that on. Thus, the acceleration of gravity at the surface of the Earth, G, is determined by mass of the Earth and radius of the Earth. So we don't confuse the big G with the little g. Little g, of course, is the 9.8 if it's at the surface of the planet. Until G was measured, the mass of the Earth was not known. But once G was measured, the universal gravitational equation could be used to figure out the Earth's mass, and Cavendish was the first to do so. So in an earlier video, we looked at manipulating that equation to do it. If we knew what the radius of the Earth was, by looking at Eratosthenes, what he did, we could then figure it out. If we use G equals 9.8, just disregard the negative, just simply look at the magnitude of G and the radius of the Earth, then from the universal gravitation we get me. So rearranging this, multiply each side by re squared divided by G, we get the mass of the Earth, 5.98 times 10 to the 24. Note the radius of Earth had been previously calculated, as I mentioned earlier. So with that, the previous equation can be applied to other planets as well, where G, M, and R refer to that particular planet. Okay, so we'll do an example here. Estimate the effective value of G. So at the surface of our planet, we take it as being 9.80. But of course, there's different elevations on Earth. So how does that fluctuate? So estimate the effective value of G on the top of Mount Everest, which is 8,850 meters above sea level. So the 9.8 we take as being the sea level gravitational field strength, or acceleration to gravity. That is, what is the acceleration of gravity of objects allowed to fall from that altitude of the top of Mount Everest? Ignore the mass of the mountain itself. So G equals big G multiplied by the mass of Earth, all over the radius squared. Now we have to be careful here about this. So if we're looking at Earth, for example, we have the radius of Earth. And of course, if I'm talking about Mount Everest, there's an extra piece we have to add on here. And of course, that extra piece is 8,850 meters. So the radius, the R that we're going to be using is, I'll write down here, where did I have it on the previous page? I had it at radius of Earth plus altitude, I could say. So radius of Earth, 6.38 times 10 to the 6, plus the 8,850. And that's going to give me a total of, let's say I'll maybe write it down here, 6.38850 times 10 to the 6 meters. So it adds a little bit onto that. Not a huge amount, but a little bit. So big G, 6.67 times 10 to the minus 11. Mass of Earth, 5.98 times 10 to the 24. Divided by that. Now, I know we talk about R, and it's radius, but think of it as radius of separation, or distance of separation between the center of the Earth to the center of the object. And of course, the center of the object is so small, we just simply assume its position is equivalent to the position it would be at its center. So that gives us 9.77. So it's a little bit less. Not a huge amount, but a little bit. So note that the equation does not give precise value for G at different locations because Earth is not a perfect sphere. The Earth not only has mountains and valleys, it also bulges near the equator but also its mass is not distributed precisely and uniformly. The Earth's rotation also affects the value of little g. However, for most practical purposes, when an object is near the surface of the planet, we use 9.8 for little g. And here's some examples of other places. So New York City, San Francisco, Denver, Colorado, we could see it's 1,650 meters above sea level. So the acceleration of gravity is less, Pikes Peak, etc. And of course, the further we go out, the further that altitude is. Of course, we'll eventually get to a spot where it's close to zero, the gravitational field strength. All right, so you should be able to do the assignment, and that was FI 1.2.